Alright, so I think this is recording, and I've been having some difficulty lately. Alright, so we're looking at Skill Packet 5, these exponential and logarithmic functions. In Skill 5a, we're introduced to exponential functions, and we'd like to look at the graphs of these exponential functions and see if we can define different properties like domain and range, and is there a horizontal asymptote? Is there a vertical asymptote? Or should there be any holes in the graph? You know, things like that. So in the very first problem, they ask us to complete a table and then to plot the points and connect the dots and graph this function f of x, where f of x is equal to 5 halves over x. So to get this table, we can use a calculator, and when we have this 5 halves, I would put it in parentheses so that it knows that the base is 5 halves. And now this x, we plug in the different values for it. So in our table, we've got -2. Now the calculator may give you a decimal number, and let's record that decimal number. The exact value of this, if I convert this to a fraction, is 4 over 25. So that's how I constructed this table. If I bring back what I just keyed in on the calculator, well, do it again. Instead of -2, let's put in a -1. It has a decimal number, 0.4, and you can see that one's easy to convert to a fraction. That's 2/5. If you hit 2 out of 5 free throws, you're shooting 40%. Alright, so what about this guy raised to the 0 power? Well, by definition, the calculator should recognize that 5 halves raised to the 0 power is 1. And that's by definition, so the calculator knows that. And now if we key in 5 halves raised to the 1st power, well, that's pretty easy. That's 5 halves. Half of 5 is 2.5. And now if I raise 5 halves to the 2nd power, I obviously get the 25 over 4. And as a decimal, that's 6.25. So you can see the fraction 25 over 4. If I plug in a 3, well, 125 over 8. And as a decimal number, 15.625. Well, I don't know why I'm carrying this out to a lot of digits. When I go to graph this, I'm going to be lucky to eyeball it and get 0.2, you know, even lucky to get 0.4. Like if I'm doing this freehand, my 0.4 might look like somebody else's 0.5 or 0.3. You know, you just do the best that you can. And actually on here, because I want to illustrate some things to students, I actually used a computer software, or Epert used it. One of us did when we made this key last year. So this is my table for number 1, and now we're going to graph these points, but I'm going to move on and complete the table for number 2 and number 3, and then talk about the graph with all three functions on the same graph. So if I move on to the next problem, well, I'm going to key it in just like I did before, but instead of the base being 5 halves, it's 2/5. And you can see it's a reciprocal. So you can actually see these values that this is a reflection of the previous table. So this 4 over 25 that was associated with -2 is now 4 over 25 is going to be associated with +2. And you can see that there's a reflection. If you don't see that, we can key in the values. So let's put parentheses around our 2/5. And raise this to the -2nd power. I get a decimal number of 6.25. And like I say, we saw that 6.25 is 25 over 4. So let's bring back my base, and let's change the exponent to a negative 1. I'm getting 2.5. And 2.5 as a fraction, hopefully you can see that's 5 halves. If I plug in an exponent of 0, the calculator should recognize that by definition, a non-zero base raised to a 0 power is equal to 1. And if I have 2/5 raised to the first power, well, it's 2/5. And as a decimal number, that's 0.4. If I raise this to the second power, I square the 2, which is 4. I square the 5, which is 25. I get 4 over 25. And as a decimal number, that's 0.16. So you can see we got 4 over 25. If I plug in 3 as an exponent, 2 cubed is 8, 5 cubed is 125, and as a decimal number, I get 0.064, and you can see that if I turn that to a fraction, 8 over 125. So that's how I got these values. But when I go to plot, if I'm doing it by hand, I'm not going to very likely know off the top of my head that 4 over 25 is 0.16, and I'm not going to be accurate enough to graph that to the nearest hundredth. I'll be lucky to graph it to the nearest tenth. So for this third one, this is the one that a few people had questions about in class, because you're just not familiar with that base of e. See, this base of e is similar to pi. It's an irrational number, and I must be set to 4. Yeah. That if I to 9 or 10 decimals, it's 2.7182818, so forth. And it's just like pi in the fact that they're both irrational numbers. They have a decimal number that that goes on forever without any repeats. There's no repeating pattern. It's not like 1/3 where the decimal number is 0.333, where you've got a repeating pattern. It's irrational. Its decimal representation is not a pattern. Like, see, 1/3 is not irrational. That's a ratio. So it's pretty amazing when you start getting into applications in college and studying things, that the formulas and the things that you see where pi appears and where e appears are not things that you would expect them to appear in. So if we key this in, if I put 1/2 in parentheses, and then on most of the TI calculators, the E is on the LN button, so you have to hit the shift or the second key to get there. And now if we plug in a -2, you'll see that I have a error typo in this first number. It should be 0.06. So let's, I don't know, we can just write it to 4 decimals. 0.6. Here, let's have that calculator do the work for us. If we round it to 4 decimals, like I say, I can't graph this thing by hand to 4 decimals, so I really don't know why I'm doing that. But like I say, I'll be lucky to get it to 0.1, let alone 0.06. So if our exponent is -1, let's change that -2 to a -1, and to 4 decimals, hey, the 0.1839, I don't have a typo there. If we raise this to the 0 power, well, e to the 0 is now going to be 1. So you have 1/2 times 1, which is just going to be 1/2. And as a decimal number, that's going to be 0.5. See, we see that here. Now, with 1/2 of e, Well, if E is 2.718 whatever, then it's half of that. So it's approximately 1 to 4 decimals, 1.359. If we key in an exponent of 2, so you can see how this is very calculator dependent. To 3 decimals, 3.695. Okay, and if we have this to the third power, so if we round it, 10.043. So those are the values that I got with the calculator. Now, if we take these and we plot points, I claim that you'll get something like these graphs. Now these graphs are a lot nicer because I've done it on a computer and not freehand. But let's go back and get my table, at least this first table. Let's see if it's not reasonable. Oh, that's not the one I wanted. I wanted problem 1. Did I not? I probably forgot to hit this button. Okay. So if I shrink that up a little bit just to kind of get it out of my way. Well, -2 and 0.16. Here's -2. It's kind of hard for me to tell. The 0.16 is this going to be the green graph or the red graph? I mean, they're almost on top of each other. So this point is not very illustrative. What about -1? 0.4. Well, now it's beginning to look like maybe it's going to be the red graph. When x is 0, I have 1. Well, that's clearly now going to be the red graph. And when x is 1, 2.5. When x is 1, that's about 2.5. When x is 2, 6.25. So here's 6, and yeah, I suppose that could be considered 0.25. And when it's 3, 15.6. When it's 3, here's 15. And see, even the width of this, it's hard for me to see, where it's crossing, there. Now, it said 15.6, so maybe it'd even be a little bit higher, But by hand, that's as close as I'm going to get. But I do see that this has a y-intercept at 1. I do see that it has a horizontal asymptote of the x-axis. That red graph is coming down and getting closer and closer to the x-axis, but it's never touching it. So the x-axis is the line y equals 0. I see that it's an increasing function over its domain. The domain is from -infinity to +infinity for all exponential functions. The range is 0 to infinity. Like I say, it's an increasing function. So there's a lot that I can tell when I have the graph of a function. There's a lot of property. It doesn't have any x-intercepts because the horizontal asymptote is y equals 0. So it never touches the x-axis. Okay. So let's now come and take a look at the table for number 2. We know that the table for number 1 was the red graph. So let's clear this and take a look. Let's get rid of this guy. And let's go get that graph for number 2, the table for number 2. So when it's -2, the 6.25, well, when it's -2, 6.25 looks to be about right there. So immediately I can tell that this problem number 2 is going to be the blue graph. At -1, 2.5. At -1, 2.5. At 0, it has a y-intercept of 1. At 1.4, well, that's a little bit hard, that's a little bit harder to see. It does look like it's around half the distance, so at least the 0.4 is close to being right here. 0.16, well, now I don't really have a way of recognizing if this is 0.16. And the 0.064, good luck there. I mean, that's basically telling me that it's almost on the x-axis but not touching the x-axis. So if I look at this graph, it doesn't have an x-intercept just like the other because it's getting closer and closer to the x-axis and not touching it. It has a y-intercept of 1 just like the red graph did. Its domain, because it's an exponential function, is all real numbers. And the range is entirely above the x-axis, so the range is positive real numbers. But instead of being increasing, as x increases, the y values are going down. So this is a decreasing function. Alright, so, and the horizontal asymptote, we said it was the line y equals 0, or the x-axis. So those are the things that they expect us to observe from a graph. And the difference, with the primary comparison between the red graph and the blue graph is the red is increasing, the blue is decreasing, and their reflections are symmetric with respect to each other with respect to the y-axis. If we reflect the red graph across the y-axis, we get the blue graph. So we can see that also from the equations. If we have 2/5 and we reflect that, then that negative sign flips this fraction, 5/2, and so this 5/2x is a reflection of this graph, and that's what we see here in the graph. Now, what about this green one? Well, remember the green one was the exponential. So let's see if we can't recognize the green versus the red here, if we can tell the difference. So when x is -2, over here I really can't tell the difference between the red and the green. So this point at -2 is not very helpful. At -1, it's kind of the same thing. I'm starting to get 0.2, and it's hard to tell for certain what should be going on there. But when I get at 0, I know that the red graph had a y-intercept of 1, and this one has a 1/2, and that's getting a lot more clear from the graph. So I'm really beginning to see now that this 1/2 e to the x is this green graph. And if we go and plot the rest of these points, 1 and about 1.4, 1 and about 1.4. Well, I know up here the red one would be bigger than 2. So I know that, I'm just eyeballing the 1.4 there. For 2, 3.695, about 3.7. Well, here's 3. 0.7 is going to be just below the 4. So that seems pretty reasonable. So the computer did a good job, which we would expect. And this is going to be about 10. When 3 here at x equals 3, that we're getting a little bit 10.043. Well, that's so close to 10, I can't eyeball that. So definitely this problem number 3 was the green graph. So, the primary thing that told us the difference between the green and the red was the y-intercept, I think. If you don't have any transformation, any kind of a vertical stretch or shrink, and you're not lifting the graph up or down, then I knew that the what was it, the 2.5 to the x, I know that 5/2 raised to the 0 power is 1. I know it has a y-intercept of 1. And I know this guy, e to the 0 is 1, and 1/2 has a y-intercept of 1/2. So that really illustrated the difference here on the different y-intercepts. And then, if I was doing this by hand, I would just have to plot the rest as carefully as I can. And by hand, you're not going to be able, it's not going to look really nice probably on your paper when you're doing it freehand with the red and the green because they're so close to each other. So anyway, the red and the green were increasing. Um, the green has the same domain as the red, all real numbers. It has the same range, positive real numbers. Its y-intercept is different. It's y-intercept of 1/2, but it's an increasing function, and its horizontal asymptote is the same, the line y equals 0, or in other words, the x-axis. So I hope that helps with problems 1, 2, and 3. If you have more questions, you can definitely ask me. Talk to you later.